All right, kiddos, the last thing I'd like to talk about today is Coulombs Law. So Coulombs Law is the equation that we use to calculate electrostatic forces between two charged objects. Okay, so Coulombs Law looks a whole lot like Newton's universal law of gravitation. So electrostatic forces are written F sub E. And the equation is a constant. This is a lowercase k times the absolute value of two charges over how far their centers are separated squared. Doesn't that look familiar? It's a very similar shape to Newton's universal law of gravitation, and we'll do an explicit comparison here in just a little bit. All right. Another way that this is written, kind of like Newton's universal law of gravitation, is instead of Q1 and Q2, we could write Q, lowercase q, and uppercase Q over R squared. Okay? And then this K is kind of like our uppercase G, Newton's universal gravity constant. This lowercase k is called Coulomb's constant, and it is 9 times 10 to the 9. Super easy to remember. Newtons, oops, that's a N. Newtons times meters squared per Coulomb squared. All right. So go ahead and box these things in your notes. Okay, be super duper important. All right. Now, just like there was gravitational field strength, little g, there's also electric field strength. All right, so electric field strength, electric force. Do you guys remember how gravitational force? Well, here, I'll just write it this way. Electric force is equal to charge times electric field strength. Remember, the force due to gravity was equal to mass times gravitational field strength, right? So we've got our field strengths here, and then the force was interacting with gravity, it was interacting between masses, and here electric forces are interacting between objects with charge. Okay, so they're set up the same way. Okay, with gravity, we could say gravitational field strength was equal to the force due to gravity divided by mass, right? And electric field strength, we can say electric field strength is equal to the electrostatic force divided by charge. Okay? So if we were to do that, take the electrostatic force, K times Q over R squared divided by Q, right? These Q's would cancel, and we would get electric field strength is equal to K times the, times the larger Q over R squared. So we can write it this way, or we could write it this way. So these are all equations that will be helpful to have in our pocket. Okay. So let's set up this graphic organizer that will be super handy in explicitly comparing forces between charges, right? Static charges and forces between masses that are interacting gravitationally. Okay, so let's do Coulomb's law again. Force, electrostatic force is equal to K times Q over R squared. Okay, electrostatic forces, depending on whether the both charges are similar, or if they're opposite, these forces can attract or repel. Okay. Newton's universal law of gravity, Fg equals big G mm. Actually, let's write them the other way around. Mm over r squared. Okay. But can gravitational forces repel? No, I want to kind of think about that for a second. Oh, that would be weird, huh? So gravity is only attractive. But look at these equations. They look super similar. Okay, now let's take a look at the constants. Coulombs constant, 9 times 10 to the 9 Newton meters squared per Coulomb squared. And Newton's universal gravity constant is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And you should see that Coulomb's constant is way, 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 way bigger than the universal gravity constant, which means forces between charges are much more significant compared to gravitational forces. All right, and then gravitational field strength compared to electric field strength. Electric field strength is Q over r squared, right? Or electric field strength is electrostatic force divided by charge. And the units, force divided by charge, so it's newtons per coulomb. Field strength for gravity, little g is big G, big M over r squared, or the force due to gravity over mass, and it is in units of newtons per kilogram or meters per second squared. All right, so this will be a really handy thing to kind of have in your back pocket, because I guarantee on the IB exam for questions related to this topic, they will ask you to explicitly compare these two forces. All right, I do want to do an example just to show you how much more significant forces between charges are compared to forces between masses. So let's say we've got two objects that are 1 kilogram, right? The standard SI unit of mass. And each of them also has an electric charge of 1 coulomb each. One object is positive and one is negative, all right? And they're separated by 1 meter. And I want to compare the magnitude of the attractive forces, electric and gravitational. We know that they'll be attractive because gravitational forces are always attractive. And we also know that our objects have opposite charges, and opposite charges attract. All right, so let's calculate the gravitational force first. So big G mm over r squared, 6.67 times 10 to the minus 11 times 1 kilogram times 1 kilogram over 1 meter squared. Okay, so that means two 1 kilogram masses separated by 1 meter exert a force on each other of 6.67 times 10 to the minus 11 newtons. Right, really super small amount of force. Okay, if small masses exerted a significant gravitational force on each other, I want you to kind of imagine what our world would be like, right? Walking around would be inconvenient. All right, so let's take a look at electrostatic forces. K, Q, Q over R squared. 9 times 10 to the 9. Whoops, that's an exponent. Times positive 1 Coulomb times negative 1 Coulomb over 1 meter squared, and we get an electrostatic force of 9 times 10 to the 9 newtons. Right. So if we just look at the standard units of mass, 1 kilogram, and how that those two masses impact each other gravitationally, and we take a look at two standard units of charge, 1 coulomb separated by 1 meter, we see that the force that is exerted between the two objects based on their charge is much more significant. 9 billion newtons of force, right? 1,000, million, billion, yes, 9 billion newtons of force. I want you to give you some perspective. 9 billion newtons is about 2 million tons of force, which is about 720 times the thrust of a space shuttle booster during liftoff. Isn't that rad? So that what it tells you is that one, you probably don't want to experience two things that have a charge of 1 coulomb. Right? Don't put them anywhere near a meter together, right? The attractive force or repulsive force that they exert on each other will be significant. So 1 coulomb is a whole hell of a lot of charge. Okay. All right, there are a couple of examples that I would like to take a look at. Two figures have, there are two figures. The first example is we've got 3 charges. Determine the magnitude and direction of the net electrostatic force on Q1. Okay, so we're looking at this guy. All right, and then another example is what is the direction of the net force on the middle charge. Okay. All right, I'm going to pause this. I would like you to consider both of those questions. And then when we restart, you should be able to check your answers. Okay? All right, hopefully you've had a time to consider both examples before continuing with this video. So I tried to color code these. So we're looking at the force acting on the center charge, right? So Q1 would experience an attractive force, right, acting towards Q2, right, because Q2 is negative and Q1 is positive. We're just looking at the forces acting on Q1. It would be attracted to Q2. Q3 is also negative, so Q1 would be attracted to Q3 as well. All right, so what we need to do is find the forces that are being exerted between Q1 and Q2, and then the forces that are exerted between Q3 and Q1, right? And then find the difference. And so that's what we did, and you can pause this to take a look at my work here. And then I noticed that the force acting between Q3 and Q1 was bigger, so we have take that and subtract the force between Q1 and Q2, and we get a net force of 5.7 times 10 to the negative 6 newtons to the right. All right, and then here are the answers for the second example. Okay, please take a look at the color coding so that you can see each charge and the force that's exerted on the middle charge due to it. Okay, and then the net force. All right. Okay, so your homework this week, take a look at Chapter 18, Sections 1 through 5, a couple conceptual questions and a couple problems. Please let me know if you have any questions. All right, have a good week, everyone. Bye-bye.